We're going to now run through the calculation all the way into the brain. I'm just going to pause here in case there's anything you want to see with this screen about the quantities we're going to use. And then I'm going to clear the screen and start the calculation. So let's go ahead and get a new canvas. No. Let's fill it with black. Bring up the white pen. And away we go. What happens first? Okay. First we have air scalp. This is Z2, this is Z1. The reflection, we have incident wave EI of the value that we calculated earlier. Where was it? 470 volts per meter. That's what's coming from the cell phone through the air towards the scalp. Let's look at the transmission. So that's going to be the transmission coefficient times the incident electric field, and the transmission coefficient is going to be equal to 2 times Z2 over Z1 plus Z2. That equals, if you run through the numbers, because this characteristic impedance is, what was it, 55, and this equals 377. Just plug and chug. This is going to be 0.255. Okay, that's the transmission coefficient. The reflection coefficient is going to be Z2 minus Z1 over Z1 plus Z2 equals 55 minus 377 over 55 plus 377, and that equals 0.75 roughly. Okay, let's go on to the next boundary. The next boundary is going to be between the scalp and the skull. And this boundary is a little more interesting in one way. So the incident electromagnetic radiation here is incident upon the boundary. We have the transmission, the transmitted field equals transmission coefficient times EI. In this case, Z naught equals 145 ohms. Over here for the scalp, Z naught is above equals 55 ohms. So the transmission coefficient equals 2 times Z2 over Z1 plus Z2 equals 2 times 145 over 55 plus 145. If you do the math, that comes out to be 1.45. Okay, greater than 1. Remember, the conservation of energy does hold, and I'm going to prove it to you right here. We have the reflection, ER, so which is the reflected going wave, ER equals EI times the reflection coefficient. We know the reflection coefficient equals Z2 minus Z1 over Z1 plus Z2. In this case, that's equal to 145 minus 55 over 145 plus 55, which is equal to, I got it calculated here, roughly 0.45 positive. Both these quantities are positive. The transmission coefficient, you'll note, is always positive. The reflection coefficient can either be positive or negative depending on if there's a phase shift. Okay, conservation of energy, does it hold? Well, we know that EI over Z1, EI squared over Z1, should equal ER squared over Z1 plus ET squared over Z2. Let's plug our quantities in. So this equals 0.45 EI squared over Z1 plus, what was it, 1.45 EI squared over Z2, and this, we cross out the E sub I is the incident electromagnetic wave, and we have 1 over Z1 equals 0.45 squared over Z1 plus 1.45 squared over Z2, where Z2 is equal to 145 and Z0 is equal to 55. Z1 is equal to 55. So this one is equal to, what did I say? 145 ohms. This is equal to 55, and this is equal to 55. And if you were to just run the math here, you're going to find that the two sides of this equation are equal. Let's go ahead and do that. So we're going to have okay, we're going to have 0.8 over 55, moving all these terms to the left, and over on the right we're going to have 2.1 over 145, and this comes out as 0.0145. It's approximately equal to 0.0144. With all the roundings that I did, that's equal for all intents and purposes, and so the conservation of energy holds. So there was not amplification of some sort. Okay, there's one last boundary after the skull going on. The last boundary is the skull brain boundary. And here I'm just, so we have the incident wave, we have the transmission wave. I'm not going to worry about the reflected wave. I'm not going to calculate that. The transmitted portion is going to be, again, the transmission coefficient times EI, E sub I, and the transmission coefficient is 2, the Z naught is about 50. So the transmission coefficient is 2 times 50 over 50 plus 145, where Z1 is equal to 145 ohms. Okay, that comes out to be 0.51. Right. Okay, let's put it all together. Putting it all together, we had the initial wave impinging on the scalp as 470 volts per meter. That went through the scalp and then the skull. Let me write this a different way. Let's put this 470 volts per meter. It went through the scalp, the skull, and then finally at the brain. The brain. And at each step there was a transmission coefficient. For the scalp, the transmission coefficient was 0.255. For the skull, the transmission coefficient was 1.45, and for the brain it was 0.51. So all you need to do is multiply this by the other three quantities. So we have multiplication here, multiplication there, and multiplication there. And it comes out to be the electric field that makes it into the brain is 89 volts per meter. 89 volts per meter. Now, all we have to do, when we're almost there, is determine how that decays in the brain and does it meet the FCC standard. Okay, I'm going to, do I have time to do that here? I'm going to do that in the next video.